Welcome back. We're in chapter 9, section 3, talking about the hyperbola. Um, and just to jump right in, let's go ahead and slide down our notes to the vocab, and we'll ping pong back and forth and label each piece in our drawing. But first things first, definition of a hyperbola, very similar to the definition of an ellipse, except that hyperbola is a set of all points in a plane whose the difference of the distance from two fixed points, the foci, remains constant. If you recall, the definition of an ellipse was the sum of the distances to two fixed points, the foci, remain constant. The foci are always going to lie on our what is called our transverse axis, and the distance from the foci to the center we are going to call c. And to find c, we can use the equation c squared is equal to a squared plus b squared. Okay, the transverse axis is determined by the variable that comes first or is positive in the equation for the hyperbola. You look at the equation of the hyperbola right now is very similar to the equation of for an ellipse. However, we are subtracting. The transverse axis contains the vertices and the foci for the hyperbola. The conjugate axis runs perpendicular to the transverse axis, and it is used to draw the box for constructing the asymptotes of the hyperbola. Lastly, the asymptotes of the hyperbola, as with any asymptote, they describe the end behavior of the hyperbola. The slope of the asymptotes will always be plus or minus b over a, where b and a come from the equation of the hyperbola. So let's go back up to our picture of a hyperbola here and label the different pieces that we know. So we look here, we see, okay, well, our x squared trinomial is positive here, and we notice that we have a horizontal opening hyperbola, and down here we have a positive y squared trinomial, which gives us a vertically opening hyperbola. Well, the transverse axis goes right through the center of the hyperbola, which we will call HK, just like with the ellipse and circle. And half of the transverse axis is A. The foci will always lie somewhere in the opening of a hyperbola and be c units away from the center of the hyperbola. The length of the conjugate axis, which we're just going to make one up right here, we'll call this B, is what we use to construct the box which will then give us our asymptotes. Our asymptotes will run through each corner of the box created by the transverse and conjugate axis. Perfect. And the same thing holds true down here with the vertical hyperbola, except here the transverse axis is labeled as B, so I'll label it as B, and the conjugate axis, maybe we make it right there, label it as A, and we can go from there and make our box. Not very pretty, but gets the job done. So let's jump straight into doing some examples of hyperbolas. So the first example of a hyperbola, besides the fact that the question says sketch the hyperbola, we could automatically tell it's going to be a hyperbola because we have a positive x squared and a negative y squared, and we see that we have two different vertical and horizontal stretches. So that tells us right away that we're going to have a hyperbola, and we should probably make it equal to 1. So we need to divide everything by 36 to give us the equation x squared over 9 minus y squared over 36 is equal to 1. So because the x squared term is positive, I automatically know it's going to be a horizontal opening hyperbola. So it's going to open to our left and to our right in some way. And because there appears to be no hk, we can assume that hk is 0. The center of the hyperbola is 0, 0. Okay, our transverse axis, 3 squared is 9, so we are going to go to the right 3 and the left 3 to get the vertices of our hyperbola. And our conjugate axis is length 12, which is up 6, down 6, pulled directly from the square root of 36, which is underneath our y squared term. So we can now automatically, we're able to make our box. We can quickly draw our asymptotes through the corners of each box. Notice the asymptotes go directly through the center. We can calculate where our foci are by using the equation c squared is equal to a squared plus b squared, which means c squared is equal to 9 plus 36. So c is equal to plus or minus radical 45, which is equal to plus or minus 3 radical 5. If you're struggling to understand where radical 45 is, remember that it's a little bit bigger than radical 46. Okay, and less than radical 49. So somewhere between 6 and 7 units away from the center. So there's 3, 4, 5, 6, somewhere between 6 and 7, somewhere between 6 and 7 units away from the center. And we can rough sketch our hyperbola, understanding that the asymptotes are going to describe our end behavior. Perfect. So jumping down to the next one, we can automatically see it's going to be a hyperbola, other than the fact that the question states that. But we have a y squared term, we have an x squared term. One is positive, one is negative, and different horizontal and vertical stretches. So that automatically is telling us, hey, it's hyperbola time. So we're going to go ahead and realize that in order to get our equation to look like the standard form equation of an ellipse or of a hyperbola, we're going to need to complete the square again. So remember, completing the square is simply the process of us adding our additive identity in a clever way such that we can factor a perfect square trinomial. So 9, we're going to factor off the y squared terms. Y squared minus 2y plus something minus something. We're going to factor off a negative 4 from the x squared terms, making that x squared plus 6x plus a blank minus a blank. And we have minus 63 equals 0. Completing the square is b over 2 squared. So we are going to take negative 2 divided by 2 is negative 1, squared is 1. And 6 divided by 2 is 3, squared is 9. And now we're going to have a nice perfect square trinomial. Recalling, as we are factoring, that this is not actually a negative 1. This is a negative 9. This is not actually a negative 9, but rather a positive 36. Perfect. And if we move all of our constants over to the other side, The equation of our hyperbola is starting to develop, but we need our equation to be equal to 1. So we'll divide everything by 36, leaving us with y minus 1 quantity squared over 4 minus x plus 3 quantity squared over 9 is equal to 1. So because the y term is positive, x term is negative, we see, okay, hyperbola time, and it's going to actually be a vertically opening hyperbola, so we're going to end up with a hyperbola opening up, and, well, that didn't look good, and opening down. Okay, the center of our hyperbola, this is sometimes tricky for people, but we are shifting left 3, up 1. There's the center of our hyperbola. Our transverse axis is going to go up 2 to the top vertex and down 2 to the bottom vertex. And our conjugate axis is going to go right 3, left 3 to allow us to make the box that will help us draw our asymptotes. Perfect. So we have the asymptotes perfectly drawn. We can now draw our hyperbola because we know it's vertical and we know the asymptotes are going to describe the end behavior. We're being asked to also find the foci of our hyperbola. So we need to use the equation c squared is equal to a squared plus b squared, very similar to the equation for an ellipse, but not exactly the same. So 4 plus 9, so c is equal to plus or minus radical 13. For those struggling where radical 13 is, remember it's a little bit bigger than radical 9 and less than radical 16. So somewhere between 3 and 4 away from our center. So 1, 2, 3 is about right there. 1, 2, 3, it's about right there. With our foci, I'm going to draw a little arrow here. Our foci are going to have the x-coordinate of -3, but their y-coordinate is going to be 1 plus radical 13, and the bottom foci, same x-coordinate, -3, but the y-coordinate is going to be 1 minus radical 13. Perfect. The next question is asking us to find the equation of the asymptotes for the hyperbola. Well, it's a little easier than we think. We automatically, we should know the slope. They are linear, okay? And the slope will always be rise over run, which means we're always going to be going half of the transverse axis over half of the conjugate axis for this vertical hyperbola. So our slope is going to be plus or minus 2/3. And if we go up 2 over 3 and down 2 over 3, we see our y-intercepts are very easy to see from our picture. So the equation of one asymptote is 2/3 x plus 3. And our second equation is -2/3 x, my pencil was on the y-intercept, minus 1. Perfect. One more example here, really quick. We're being asked to find the equation of a hyperbola with the foci at -8, 1 and 0, 1 that has a transverse axis that is 2 units long. So if we just want to draw a quick sketch, -8, 1, 4, 5, 6, 7, 8, 1, that's a foci. And it has another foci at 0, 1. I automatically can tell right now that I'm going to have a horizontal hyperbola. It's going to be opening to the left and right. I know my center is going to be directly in the middle, so it's going to be at negative 4, 1, which allows me to make part of my hyperbola equation right away. I can have my center at negative 4, 1, or left 4, up 1. I know it's a horizontal hyperbola, so it'll be opening left and right. I know that my transverse axis is 2 units long. My transverse axis, which means that it's a total of 2 units. So it means I'm going to have to go 1 unit to the right and 1 unit to the left of my center to find my vertices. My transverse axis is horizontal. It's going to be underneath my x term. My x plus 4 squared is going to be over 1 squared. Now I simply need to find my b term. And knowing that c squared is equal to a squared plus b squared, or c squared is equal to 1 squared plus b squared. I also was given my foci, so I can see that my distance away from the center that my foci are is 4 units, so my c squared is actually 16. So b is equal to plus or minus radical 15, meaning that my b squared is going to be 15. Leaving my final equation for my hyperbola being x plus 4 quantity squared over 1, which means I don't need to write it, minus the quantity y minus 1 squared over 15 is equal to 1. Perfect. Okay, I'm not going to go over all of the specifics around each equation. For a circle, ellipse, or hyperbola, I'll simply go over the equation of each. The equation for a circle was, to recall, x minus h quantity squared plus y minus k quantity squared was equal to the radius squared. The equation of an ellipse was x minus h quantity squared over a squared plus y minus k quantity squared over b squared equal to 1. And the equation for a hyperbola we just talked about today, very similar to the equation of an ellipse, x minus h quantity squared over a squared minus y minus k quantity squared over b squared was equal to 1, and that can flip-flop based on whether or not you have a vertical or horizontal ellipse. So answering our last question, look at these equations and dissecting without completing the square, without putting it in standard form, without graphing it, or using a graphing calculator, we should be able to tell which one is which here. So if we look at this first one, I see I have an x squared and a y squared term. They're being added together. That means it's going to be a circle or ellipse. But because I have different vertical or horizontal stretches, it's going to be an ellipse. If they're not being stretched at the exact same rate in both directions, it's going to be an ellipse. If they are being stretched in the exact same rate in the exact same directions, or in opposite directions, then it's going to be a circle. So the next one, if we look, looks a little bit peculiar, but let's just quickly just move everything to one side and make it equal to 0. So if I got 3x squared minus y squared plus 2x plus 2y minus 5 equals 0, I can tell really quickly that now I have an x squared and a y squared, different horizontal vertical stretches, and I'm subtracting. I'm going to be dealing with a hyperbola. Jumping down to the next one, we can move the 7 over, or you can just visualize that it's a minus 7 on the left side and see that I have an x squared and a y squared term added together. Here I have this exact same horizontal and vertical stretches, so I know I'm going to have a circle. Lastly, this one looks a little peculiar, so I'm going to go ahead and just move everything over. 5y squared plus x squared plus x minus 3y minus 6 equals 0. I can see right now that I have an x squared and a y squared term added together, but different horizontal and vertical stretches. So again, I'm going to have an ellipse. Awesome. Thank you so much for listening. I look forward to answering your questions.